Okay. All right. So today I have a few ideal diode problems. Um, First up is, well, there are two circuits, and we look at determining the output characteristics as a function of V in. And in the next two, it's a straight up, um, well, straight up, not straight up, but it's kind of like a digital circuit. Okay. So let's take a look at the first one. So we have the Zener regulator, and this is, okay. All right, so let's add one more page is to ideal diode. Samples. Okay. All right, so let's say we have a circuit like this, which is one diode and then output. V in of t. Then let's see another resistor here. And this would be your V out. And this is V in. Okay. R1 is given as 1 kilo ohm. R2 is also 1 kilo ohm. And diode D1 is an ideal diode. Now, if you remember, ideal diode or constant voltage drop model, which requires 0.6, 0.7 volts, the analysis remains the same. It doesn't change. Okay. Question being asked is determine the transfer characteristics transfer simply means output to V in, output to input, ratio of output to input. It's also the transfer function, right? Transfer function, H of F or H of omega, H of j omega, transfer function, V out or V in. There's no other information given, and we don't need any other information. And then let's say my transfer characteristics. And plot it. Plot V out or V in. Okay. All right. So assuming ideal diode, we are not given anything. So we don't know whether V in is AC, DC. We have no idea. So you simply make an assumption. V in is an AC signal. It could swing positive and negative peaks, right? So if it's a positive peak, then a representation can be made that there's plus at the top, minus at the bottom. If it goes negative peak, minus at the top, plus at the bottom. So let's do this. If V in is AC input, then in positive half cycle, circuit's going to look like this. Let's make it representing as a DC source, but I mean, I'm representing it as a battery, so not a DC source. It's a battery. But for all intents and purposes, if it's in the positive half cycle, doesn't matter what its value is. If it's going from, for example, if it goes from 0 to plus 5 volts, it will still be positive for all values in the positive half cycle. So it goes 0, 1 volt, 2 volt, 3 volts, 5 volts, and then come back down to 0. But the positive will always be at the top. If that's the case, then the anode is always forward biased with respect to the cathode. So the diode will always be on. Hence, it would behave like a short circuit. So it doesn't matter if V in is DC or whether V in is AC. If it's positive half cycle, diode is always forward bias, meaning it's always on. It'll always behave like a short circuit. Okay. So what is V out? Is that correct? I had one student say V in. Is that correct? Just straight up look at the terminals for VO and V in. Terminals are exactly the same. So V out is equal to V in. So if you apply 1 volt, output is 1 volt. If you apply 2 volts, output is 2 volts. If it's a sine wave, output is exactly the same. Ideal diode, no resistance whatsoever, no drop, right? If you apply a triangular wave, you're going to get a triangular wave output. So it doesn't matter what it is, V out is equal to V in. All right. So now let's look at what happens when it goes negative. So the negative cycle what do you think happens in the negative cycle? Diode is off. And so it behaves like an open circuit. So what is VO now? Voltage across. Murmurings. I should ask your 201 instructors to take your grades back. It's R1 and R2 in series. It's a voltage divider network, and they are the exact same value. So V out is a fraction of R2. So VR2 and VR2 would be a fraction of V in. And the fraction is given by R2 or R1 plus R2. In this case, since both resistors are the same value, it would turn out that V out is 0.5 times V in. So V in is 1 volt, your V out is 0.5 or minus 0.5, I would say. I should say minus. So if I was to plot this, V out as a function of V in if V in is 1 volt, my output is 1 volt. If V in is 2 volts, output is 2 volts. If V in is 3, output is 3. V in is 4, 5, output is 4, 5. Dot, dot, right? Positive half cycle, V out is equal to V in. Make sense? Right. In a negative half cycle, when V in is, let's say, -1, -2, -3, -4, -5. So -1, -2, -3, -4, -5. Again, the minus just indicates is a negative half cycle. That's all. My output, V out, would be minus 0.5, -1, 1.5, -2, -2.5, and -3. So first one would be here, second would be here, third one would be here, fourth one would be here, fifth one would be here. Output should look something like this. V out is half of V in. All right, let's take a pause while you write it down. Let me know if you have any questions. Yes. So the question being asked is if we are stating that V out is minus of V in, would it be in the second quadrant? Well, the minus sign is simply indicating the negative half cycle. That's all it means. It doesn't mean anything else. So if you look at the absolute value of any point in V in, let's say it's a sine wave, right? So V in, let's say V in varies from 0 to 5 volts in the positive half cycle and 0 to 5 in the negative half cycle. 0 to 5 in the negative half cycle mathematically would be represented as -5. And that's all it's indicating. If I understand your question correctly, V out. Okay, you're asking this mathematical expression where V out is minus 0.5 V in. No, that still makes sense, at least to me. Hold on. Yeah, go ahead. Okay, I see. Okay. Thank you for the explanation. So you're saying if V in is -5, and then I'm saying V out is also minus of -5, wouldn't it be V out is equal to +5? Okay, that also makes sense. So let me write this. This negative I is simply indicating negative half cycle. Okay, but yeah, you're right. And you're right, Veronica. So V in is V half. I mean, V out is half of V in. So if V in is -5, then V out is minus 2.5. But yeah, if you have a minus sign in the front, then it would be minus of minus. And then it becomes a positive. Did everybody understand the question? Unlike me? Yes. Okay. Any other questions? All right. So, let's see. Let me add another page. Instead of doing the same pages, let's add. Okay, this time, let's make things interesting and add a Zener diode. So now, okay, so we have that. And V out is still there. And V in. There. Okay, so that's D1. And let's call this D2. Okay. And the Zener diode D2 is, let's say, 5 volts. So ideal D1 and D2 are both ideal devices. And VZ for D2, let's say it's 5 volts. Okay, 5 volts. So then our V out is measured between these 2 points. And the question again is determine V out. Determine and plot the transfer characteristics of V out and V in. Okay, so V out as a function of V in. So how would you approach this problem? D1 is easy or straightforward. Let me not use the word easy. Straightforward. Ideal diode analysis. So if it's forward bias, it's a short circuit. Reverse bias, it's an open circuit. So similar to the previous one. How about the Zener diode? What happens in forward bias? It's a short. Absolutely. I mean, the forward bias region, a Zener diode behaves like a regular diode. So an ideal Zener diode would be on, be replaced with a short circuit. It's the reverse bias that we have to take into account. So when it is reverse bias, what happens? Below 5 volts, it's off. Above 5 volts, it's on. And that's how you would approach it. That's it. So if you keep these basics in mind, you'll be fine in the final exam, at least for one problem. All right. So again, using ideal diode analysis, D1 and D2 are both actually are on in forward bias, D1 off in reverse bias. Actually, that should D2 off in reverse bias. If V in is less than 5 volts. Okay. Greater than equal to plus 5 volts. But the key thing here is forward bias, it's a short circuit. Reverse bias, it'll be off until V in is greater than or equal to the VZ value. Yes. Question being asked is forward bias the positive? That depends on the circuit configuration. This is just in general or overall principles, because this is true no matter what the circuit is. If a diode is forward bias, it's on. If the diode is reverse bias, it's off. For this particular circuit, D1 and D2 are on in the forward bias. We haven't yet determined when they are forward and reverse bias. So that is in the next step. Okay, so the question being asked is about forward and reverse bias. The first thing is just setting it up. In general, if diodes are forward bias, we say they're on, replaced with a short circuit, and when they're off, open circuit. But Zener diode would be a special case where the reverse bias would depend on the input that's being applied. So when V in is below VZ, the diode is off in reverse bias. And again, in reverse bias also, the same secondary state would be when V in is greater than or equal to VZ. That's when it behaves like a voltage source. Yes. No, just 5. Where? The last one. Actually, you know what? So let me do it this way. In forward bias, D1 and D2 are on. And for reverse bias, this way. So you're asking about this? No, that's greater than or equal to 5 volts. Greater than or equal to. Yes. Yes. So the question being asked is if there was a voltage, I mean, if there was a resistor in series with which one? There will still be R2. You can add it to R2. So if there's a resistor here, electrically speaking, it doesn't matter where you connect that resistor as long as it's in series. It could be a 100 kilo ohm resistor. You add it to R2, it becomes 101 kilo ohms. Schematically, we can say it's before or after the Zener. But electrically speaking, when you take the equivalent circuit, it doesn't matter where it's connected. Okay. All right, so let's take a look. Ideal diode analysis, and then positive half cycle. The circuit should look like this. Okay. D2 is also a short circuit. So once again, what is V out? V out is equal to V in. Negative half cycle, what happens? Now D1 is open. Then D2 depends on the value of V in. So we can say this state or this circuit is for values of V in less than 5 volts in the negative half cycle. And what happens then for V in less than 5 volts? D2 is going to be open. So then what is V out? Redraw the circuit. without the open circuits and the branches that are redundant now, what V out do you obtain? Sorry, what? One answer is voltage across R1. Is V out measured across R1 though? It's taken at, so another possible response is 0. So the voltage is taken at one end of R1, but it's not quite across R1. All right, let's go back to chapter 2 of E201. Or the first week of 321 for that matter. If this is a Thevenin voltage, and this is my Thevenin resistance, what is the voltage here? V out is equal to V in. Let's take a pause while you think over that. Let me know if something doesn't make sense. Essentially, when you find a Thevenin voltage, Thevenin circuit, or just in general, is there any current flowing in the circuit? There is no pathway, so current is equal to 0. If current is equal to 0, what is the voltage drop across RT? Is 0. If the voltage across RT is 0 volts, what does that mean for the node voltages at either ends? It's the same. Hence, voltage at this node at the output is exactly the same as the voltage at that node. And this is an easy experiment you can perform in the lab. Take a DC power supply, clamp a resistor to it. You don't even need a breadboard. And just measure the voltage between the negative end of the power supply and the open end of the resistor. And we should, if you apply 5 volts, you should get 5 volts. Okay. So again, when the circuit is open, if you have a resistor with an open terminal and you measure the voltage, it'd be exactly the same as the other end of that resistor. Hence, coming back to our problem, explanation is in the negative half cycle, both diodes are reverse bias, but the Zener diode will remain off until V in crosses its Zener voltage. So below Zener voltage, diode remains open. If diode is open, V out is equal to V in. Make sense to everyone? So now let's look at the case, negative half cycle. For V in greater than or equal to VZ. In this case, VZ is 5 volts. Diode D1 will be open. And this time V in is greater. So V in is greater. What is the voltage? And the Zener diode turns on in the reverse bias. How can we model the Zener diode? If it's a short circuit, then the voltage across the Zener goes to 0. But the Zener diode holds the voltage constant across its terminals. If it's a constant voltage, it means it's a DC supply of 5 volts. Simply turns on in the reverse bias, and the value would be equal to the Zener value. If it's a 6 volt Zener, VZ is equal to 6 volts, V out is equal to half of V in. Okay. So if we plot this, and let's do it. So right, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm going to draw the dots this time. Just going to go linear line, 45 degrees. V out, V over V out is equal to V in. So slope is 1. Same thing here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. So until it reaches 5, the line is linear. And after that, 6, 7, 8, 9, it's going to be half, half. So here, it's 1, and here, it's minus 0.5. Yes. It's a voltage drop of 5 volts across it. So this would form, you had the same question? So in this case, we are simply using whether VZ is turned on or not. Okay, that's all we are looking at. So wait, let me redraw the circuit. And it will turn out to be like this. So minus plus, this is V in. This is VZ in series R1, R2, and I'm taking my V out across R2. So V out is here. So R1, R2. Okay, so this is now 5 volts. So if V in is equal to 5 volts, that's 10 volts being applied. So V out is equal to V in. Okay, what am I missing? I know I solved this. Output's taken across the negative end of the zener. Oh, wait, so it's not like this. Do it incorrectly. R2. And then so plus minus. And V in minus 5. And V out. So V out would be intersection point plus 5-volt drop. Maybe did I make a mistake in taking my V out? No, V out is still across the zener. So it'd be V in times R2, R1 plus R2 plus 5 volts. I'll have to take a look at this again. I was pretty certain I had it solved. So R1 and R2, it's half of V in plus 5 volts. Half of V in plus 5 volts. So if it's half of V in plus 5 volts, and if V in is 1, everything will be shifted by 5 volts. So if you apply a sine wave, it will simply follow the same shape. So the AC waveform V out would be half of V in, but it'll have a DC component to it. So everything will be shifted up by 5 volts. There's an example. So that's a good observation. Question being asked was, if the zener diode requires 5 volts to turn on, how are we taking it as a short circuit? So it cannot be half of V in. That was the question being asked. Okay. So the answer is, yeah, the question is correct. We have to take the zener diode voltage into account. And if you take the zener diode voltage into account, the output V out would be 0.5 V in plus 5 volts from that zener. So if you apply a sine wave of, let's say, let me work on this here. So if this is, let's say, plus 1 volt and not plus 1, plus 10 volts and minus 10 volts, my output should be, if this is V in, then V out should be half of that. No, actually, no. It would be 10 volts in the positive half cycle. So it'll still be plus 10 volts. And in the negative half cycle, V out is half of V in plus 5. So it shifts. I'm confusing myself. Minus 5. It's off. So V out is off. And V in would go to 10 plus 5. No, there is no V out. It's below 5. So V out would be clipped. I have to think about this outside of class on how the waveform would function. So the equation would be 0.5 V in plus 5 volts. The zener diode voltage, basically, reverse bias. That's what it would be. Good point. Did that make sense to everyone? I mean, I confused myself, and I've confused you all too. Did the analysis up to this point make sense? Right? VZ is 5 volts. Once it turns on, then we have added that voltage to our V out. Okay, yes. That's positive half cycle. Yeah. Positive half cycle, V out is equal to V in, right? That's right here. So that will remain the same. With negative half cycle, it changes. So V out as a function of V in would be a straight linear line at 45 degrees. And in the negative half cycle, V out will be equal to V in until it crosses 5 volts. Once it crosses 5 volts, then the diode turns on. And then it would be half of V in plus 5 volts. What was your question? Okay. We are actually, yeah, we are out of time. Oh, I thought I had more time to do one more example. All right, so I'm going to leave the next 2 examples for Friday. And we'll end class here today on this one. So that gives me a few more minutes to think on this. Or maybe I'll say Veronica had me in knots. I thought I had it solved. I just never plotted the V out. I was just looking at the transfer function. So, all right. So let's say I'm going to stop recording.